cloud. Before we do our last lecture here, I want to talk a little bit about the final because I have had some people asking about the final exam and how and what. It turns out, I guess I should write this down. Oh, I need to shrink that down. Why is it the wrong size? That's really weird. And I should probably also look at, oh, it would help if I shared, huh? Oh, silly me. There we go. Let's get my participants list up here. So some people have been asking about the final, so I might as well go ahead and start talking about that a little bit so we can all start getting prepared. So it looks like my 121 kids wanted to take the final on Thursday if at all possible. And I'm like, well, we're always Monday and Tuesdays for 110 and 120. And it turns out this semester they moved it on us. So 110 is supposed to be on a Wednesday. So final exam talk. All right. So it's going to be Wednesday, the, what is that? 27th. So I was right on our syllabus. Wednesday, 5/27. It was supposed to be from like 7:30 in the morning to whatever. I should probably, I hate to say this, but keep that time frame. And I know that kind of sucks for a ton of people, but I'm worried about running into other people who are going to do their synchronous time for their final. Now, before I completely commit to that, I do want to say that I'll have to talk to my department and my dean to find out if that's truly the protocol or if we can do a semi-asynchronous final where we don't have to wake up at dark 30 to take this thing. So Friday, 5/27, time is either 7:30 a.m. or TBD. We'll let you know soon. Okay, so that's the first thing. The second thing that everyone is always wondering, yes, cumulative. That means it is over everything that we have done. Next question. 100 questions. Next questions. 120 minutes. Next question. How are we supposed to get through all this? Blah, blah, we didn't have enough time on the something and okay. So let me just tell you, the final exam is designed to test your overall knowledge about the overall subject, about everything that we've done. The exams hitherto have been to test your knowledge over that section, which means I can ask tougher and more in-depth questions there than I could on a final. Clearly, if we've taken 6 exams and they each have an hour on them or so, I can't expect you to take something and get it done in 2 hours if it were as hard as the ones that took 6. So the questions will be a lot more generic, less detailed, and the test, can you do the job, not can you do the job really like super well. So to give you an indication of the type of question I might ask, and I'll tell you right now, one of them is, how many milliliters are in a liter? That's one of the questions. If you have to think more than like 5 seconds and find 1,000 and click that button, then we got a problem. What that means is that has saved you like an entire minute to do one of the longer problems where it might take some setup of math and such, say a mass to mole to mole to mass. So I have balanced it between ones that should take you 5 seconds and ones that should take you 4 minutes. And so you will have plenty of time to do this exam. 100 questions, 120 minutes. Yes, some of the questions will be that easy. 1,000 mils is equal to 1 liter. Okay. There will be things that are that easy, so don't freak out. Are people being silly and typing in chat again? I mis gatos.
No, you're fine.
Oh, Nathan, you're rolling like 20 deep to stand up to me. All right, let's see. How about this? You can have a 3x5 card for notes. I will say what this means is I will give you no information. For example, 0.08206. So if you don't know the gas constant, put it on your card. So you guys can start building a 3x5 card for notes on that. It's sort of a safety net for you guys on this final. And you can use whatever periodic table you want. I don't see a way of getting a good periodic table up there. If for some reason I do figure out, I will go ahead and give you a periodic table to use. But pretty much in any sort of standard case, I would normally give this final with a periodic table, and the rest is up to you. I probably have figured out all the questions, but does anyone else have a burning question about the final? And yes, Nathan, you can type it in if you need. Am I still live?
Yes.
Yeah,
Okay,
we're here.
All right, just sometimes when I get deafening silence, and I don't know if like my internet just took a dump or not. So, all right, well, I guess that's it for the questions. And yes, the thing I'm going over today will be on the final. All right, let's talk about some organic chemistry. Now, organic chemistry is everything carbon. Except carbon dioxide, carbon monoxide, hydrogen carbonate, and carbonate. Those are still considered to be not organic compounds. But in essence, if it's got a carbon in it, it's going to be organic. Now, what I'm about to do with organic chemistry here is by no means anywhere close to organic chemistry in general. This is enough to like peek behind the curtain to sort of get a general something or other. So when somebody in a bio class or a future chem class says the word hydrocarbon or amine or alcohol, you will have like, oh yeah, I think I saw that somewhere. This is by no means anywhere close to the depths of the demon there of organic chemistry. Because once you start messing with carbon, carbon can do a whole bunch of stuff that the inorganic stuff can't do. Remember when we talked about the predictable versus unpredictables with the metals combining with the non-metals? Yeah, it gets a whole lot worse when you start doing carbon, because as soon as you start piling on carbons, they can start doing a whole slew of different things, and they're not always predictable. In fact, I would say many times they aren't predictable unless you really control the circumstances. So let's begin by talking about that word, hydrocarbon. Okay, a hydrocarbon is C's and H's, and sometimes O's. We'll just keep with C's and H's. Sometimes O is put there. Sometimes O is put here too. Now, some of you may be looking at that C and H and go like, oh, I get it, hydrogen and carbon. but that's not exactly where the name comes from, although it's okay in my book if you want to put that in your mind and be like, oh, hydrocarbon, hydrogens and carbons. If you recall, this guy, hydrocarbon, why is it called that? Let's go the way back machine. We set that way back machine. You guys remember this thing right here? You guys remember that? No?
Yes.
Okay, remember? That guy stuck a shield over the fire and water came out of it. The reason why it's called a hydrocarbon is because when it was all done, all that was made was ash and water. They didn't count the smoke or the fire at that point. So basically what they said is this organic material was made up of carbons and waters. Now, we all know that that's actually on the back end of this circumstance, and that is where we had that combustion. Going to make CO2 and water. That's really where the hydrocarbon comes from. You got a whole bunch of carbons and water's coming off the back end. So it's really a back way of engineering the name from a combustion reaction. Now, when we talk about hydrocarbons, there's actually 3 types of chains of carbons that are made. So these guys are called alkanes, alkenes, and alkynes. Alkanes, this is all single bonds between carbon and hydrogen. These are also called saturated. Now, the saturated is not like the saturation necessarily of like, oh, I've got as much solute in there as possible, or I've got all the water in the sponge that it can hold. This is, I've got all the hydrogens around those carbons that is physically possible. I've saturated that chain with hydrogens. Now, the alkenes, they have at least one double bond, and the alkynes have at least one triple bond. And these guys are called unsaturated. So when you move on to a bio class or something, they might say, oh, on the back of this alkane chain, or in the midst of this alkene, you'll be able to, in the way back of your brain, go like, oh yeah, alkanes, it's all single bonds, okay. Alkenes, okay, we got a double bond somewhere. And those double and single and triple bonds, they actually really do truly affect the types of chemistries that can be done on any of these hydrocarbon chains. So let's take a look at a couple of examples here about alkanes, alkenes, and alkynes. So if we look at alkanes, an alkane. I'll give a few examples. I'll do C2 H6. We actually built this in the lab. We actually were able to still do the model before all hell broke loose. That would be a carbon to a carbon with hydrogens completely surrounding each of the carbons as such. We could do C3H8. Three carbons and hydrogens all around. Again, each of these carbons having as many hydrogens as possible all around them. We have saturated that chain with hydrogens. And just because, C4H10. We'll do 4 carbons here in a chain. And we'll put all the H's around them. Now again, just as a reminder, we're doing all these carbons or hydrogens around them. We are fulfilling octets. We're sharing those electrons. Everyone's being happy. Now, just because, let's see, is that right? I'm gonna do this here real quick. So what I'm doing here, I'm drawing yet another structure here. I want to point something out about each of these. And actually, let me, I'll leave it like that. Okay. C4H10. Gets kind of fun. We point out some names here real quick before I point out what I just did. This guy right here is ethane, propane, butane, and isobutane. Now, as I've named them, you may notice something very similar between all of them. Maya, what do you notice?
They all end in "ane."
Yep. And they all end in ane because they're all an alkane, right? These end in ane. One of the nice things about organic chemistry, when it's done right, or when it's named correctly by the people that are there, is that they'll follow the naming convention that sort of tells you what's going on right now. So since these all end in the suffix of ane, that means they are all alkanes. That means that they all have as many hydrogens around them as possible, even in this isobutane. The fact of the matter is this central carbon right here can only have that one extra hydrogen, so it takes it and it is saturated with the amount of hydrogens it can have. Meanwhile, the other ones, instead of having 3s and 2s, these guys can all have 3s around each of them. Now, the interesting thing about alkanes is they all follow a mathematical formula, if you will, and it's always CnH2n plus 2. So whatever number you want to put in for n, you just double it and add 2, and you'll have the rest of the H's that would apply to the alkanes. All right. Questions so far? All right.
I just have sorry, this
Yeah.
is Reagan. On the ISO,
Okay.
you put the fact that you put that fourth carbon above the main carbon.
Oh yeah, thank you. I forgot to mention that.
Yeah.
So this is what we call an isomer. It means same unit. This is when essentially, remember your resonance structures? When you could draw it more than one way? Same idea. It's the same number of atoms arranged differently. Same number of atoms arranged differently. And they have different properties. In fact, well, I'll just leave that. They do have different properties. They have different boiling points. They have different chemical reactivities. And so even while they're the same, they are different in many respects, like twins, if you will. But I would say more like fraternal twins than identical twins. So you can see very quickly, by the way, when I said, hey, we're just going to peek behind the curtain, notice that as soon as I get just 4 carbons, Mother Nature can do 2 things. And it gets even more complex as you add more and more things. And trust me, there's a lot of carbons in a lot of organic chemistry. So there are branches, there are side shoots. You can do all sorts of things as long as you keep track of all your atoms. Forget about it. And Mother Nature does that. Butane and isobutane have different physical and chemical reactivities.
So would you write this differently? So instead of just C4H10, is there some type of notation to know that's iso versus just butane?
If I just do this, no, you could draw either one. If I give you the name, it would tell you what to do. And usually the thing is, when we, so if we think back to lab, there were plenty of you that out there, we had the, I'm just going to put a little side, well, we'll just keep going. Recall from lab, just because you're making me do this. We had this CH3COOH. Okay, what I wanted you to do was do CH3 to a C, to an O, to an OH. That's what I wanted. But many of you did this. You did that, or you did, oops. Or you did this. Right? All of these are isomers. And plenty of you guys did the ones down below, and I said, you're not wrong. But then I went, whoa, it is raining like nothing instantly. Anyone else see that?
Yeah.
Dang. I was like, who's pounding on something? And all of a sudden I looked out the window. They just like deluged on me. That's cool. Sorry, I like rain. You just learned something about me. I'm a Virgo and I like rain. So the idea here, oh, not in Vallejo and the AC, maybe it's coming down to you. It's a nice gentle rain. Maybe you'll like it. I want to point out, Reagan, that if all I do is if all I did was write C2 H4O2, all are options. If I actually wrote it as like the CH3COOH, I would be telling you what I wanted, or if I gave you the name. In this case, the CH3COOH is ethanoic acid, also called acetic acid. If you recognize here that you have your H, C2H3O2, you can see the acetic acid version. This is the organic way of writing it. But if I were to make you do the other ones, I would have you do cis-ethylene diol, trans-ethylene diol, or 1,1-ethylene diol. Each of those names will tell you how it's actually supposed to be built. And before you completely lose your stuff, no, we're not going to be doing that. I'm just pointing out that it's very easy and very quickly getting into the weeds when you get into organic chemistry. Now, you can learn how to do it. It's not too terrible, but that's not the scope of this class. I'm just going to show you some stuff. And I'll tell you guys exactly what you need for the exam. So also, don't trip. All right, the alkenes. I'll give you guys a couple of examples there. And as quickly as it came, it went. Wow. That was pretty wild. Hopefully you guys get it because it was kind of cool. C2H4. Looks something like this. Well, maybe God just loves me more than it loves you, Dominique. I got the rain. Because I'm in Napa too. You're probably one of those North Nappans. Did it deluge on you, Roberto? Did it just like drop out of the sky? Yeah, that's kind of cool. All right, so C2H4, I could do a C3H6, and it would look something like this. And if we look at, ooh, what did I do the names in? Green? Purple? I think purple, right? This is ethene. And this is propene. Ooh, and I'll go to Maya. Do you notice anything about this, Maya? Anyone else notice something?
They end in E-N-E.
Yeah, they all end in, oh look, alkenes end in -ene. And also they have the formula of CnH2n. So basically we've knocked off a couple of those carbons that would have saturated it, that would have filled it around with as many carbons as possible. And every time you put a double bond on there, you actually take away 2 hydrogens in order to do that. And if we look at the alkynes, you guys sort of figure out how this is going to be going. You can have C2, H2. You guys actually built this one in lab. Actually, I think you built propene as well in the lab, and ethylene. And then we can have the C3H4, and we built this one as well. So we had a carbon, 2 carbon, a triple bond carbon, and an H with these guys. And if you haven't already guessed, this is ethyne, and this is propyne. Skip to the end, they all end in -ine. And their formula is CnH2n. H2N minus 2. Because again, adding one more bond takes away 2 electrons, or I mean 2 hydrogens. Now, what's really interesting is sort of why do we even care about the differences? All right, saturated hydrocarbons, things like propane, butane. What do we use propane and butane for?
To start a fire.
Start a fire, right? We got propane tanks, we got butane lighters, right? Their only good part is for burning. Ethine, also called acetylene. Does anyone know what acetylene is used for? It's your arc welding blowtorch. So alkanes and alkynes, sorry. Pretty much just useful burning. But alkenes, alkenes. They're a little different. These can do cool things. Let's take this guy. Let's take this polypropylene. Well, I just told you the answer. So if I draw a couple of these guys here, it turns out that what can end up happening in the mix of all this is at the end of this day, if you put two of these guys next to each other, and you put the right conditions around it, oh, I think there should be an H here, sorry. You'll end up, this guy will spring across, grab onto this guy, and create a bigger, longer chain. Two propenes chained together and they make polypropylene. It's a plastic. And actually for a lot of your synthetic clothing that you're wearing right now, if you look on it, it'll say polypropylene or PPO. Well, actually that's the oxide to make the hard plastic, but polypropylene is a lot of the really silky synthetic shirts that you'll buy. The double bonds have this ability to sort of spring out, reach to their other person across the way and make these longer chain molecules. They can polymerize. That means many units coming together. They can polymerize. Basically, this means many units they can chain together. So it is actually very important to distinguish between alkanes, alkenes, and alkynes because each of them can do slightly different chemistries, and they can result in many different products. And the alkenes are really, really useful for things like that. And then they get even cooler when you start turning them into benzene rings and all sorts of craziness, because then you can actually have them interact with light and all sorts of stuff. And guess what? We're not going to talk about that because that gets into some really long stuff that we don't want to take the time on. I'll leave that for your intro to organic and biochem courses, or your biology courses proper, or good old fashioned big girl OChem.
Can you scroll up a little
Say what?
bit? Can you scroll up a little bit?
Sorry about that. How much further? You good?
That's, yeah, I'm good, thank you.
Okay. Now, so I've just spent a few moments talking about the fact that a hydrocarbon chain is just a bunch of hydrogen carbons, and later on we'll add in some oxygens and other stuff, and you can put sulfurs and nitrogens on them, as we'll see here in a moment. But really the backbone is what we're talking about. The backbone being carbons and hydrogens chained together. Are they saturated? Meaning, oh, you can't see me covering up my screen. Which meaning, if I look at these guys right here, all these carbons have as many hydrogens around them as possible. That part of the chain would be considered saturated, but the chain overall is unsaturated because this guy is missing a couple of hydrogens. Now, you might be asking yourself, because no one's asking the question, so I'll go ahead and ask the question. Does this have anything to do with saturated and unsaturated fats? Yes, absolutely. Remember, oil and water don't mix, oil and fat don't mix. That big long hydrocarbon chain is a big oily fatty mess. And so even though the fats that we're talking about biologically are different in various offshoots of this, the concept is the same. As soon as you have a saturated fat, we're talking about that fat being just a bunch of C's and H's. Kind of hard to get in there and do any reactions. If you guys remember when you built these, it was kind of this weird zigzag and there were hydrogens sticking out everywhere. And the idea of something coming in there and doing any reaction with it is very difficult. Ooh, what just happened? But if all of a sudden you take and you just break apart this this guy and take a couple of hydrogens off it. So if we take a look here, like the ethylene or something like that, or the propylene, if you look at the carbon here on the left, if we look at it, this guy right here, there are 1, 2, 3 things surrounding it. If there are 3 things surrounding it, what is the electron pair geometry? Vincent.
Tetrahedral.
Tetra is the 4. This is the 3, so this is the trigonal planar. Now, trigonal planar means that it's flat, which means that from the top and the bottom of this molecule, or at least that carbon is concerned, it is wide open to attack. There is no hydrogen getting in the way and blocking anything. So it is very susceptible to things coming in and attacking the carbon and basically bonding with it and creating something new. So that orientation, going all the way back to your sp3s and sp2s, these guys here are the most reactive and can do the most things. Now, again, that's kind of the fun, quick backstory about what can be starting to do in OChem. But I'm going to stick to the things that I want to teach you, just so when people make names, you can sort of understand what's going on, or if people make another reference, you'd be like, oh yeah, I think I saw that somewhere. So let's talk about naming simple hydrocarbon chains. Naming simple hydrocarbon chains. And when I mean simple, I mean simple. I'm not going to do any of that thing, Reagan, where I had the 4 hydrocarbons and one of them came off the top and all of a sudden it's ISO. Although I may mention it to you guys, I'm not going to hold you to it. I just want you to be able to identify if it's an alkene, an alkane, or an alkyne, and roughly how many carbons are in there, and where things might be if they're different, say the double or triple bond. So here's how you name it. 1, name the longest chain. Now, in a molecule where you might have some side branches, you might have to track down which is the longest branch and which is not. I will just have for this exam, the chain is the longest chain. Just be aware that in bigger molecules, when you get to those classes, you may have to hunt down the longest chain. So you have to name the longest chain, and it is based on the number of carbons. Based on the number of carbons. So we're going to go through and we're going to get the names for at least up to 10. And I'm going to actually start working my way backward because the backward ones, we should already know these names, and the first 4, you probably won't. Now, why should you know the last 6 of these from 5 to 10? Well, we're scientists and we like patterns. What else have we named from 1 to 10? Let me be easier. 8. What is the name for 8 that you remember from some other naming?
Octo.
There you go. What about 6?
Sept. No, that's 7. No, sept. Oh, hexa.
Now, hexa and hepta. You were right, Reagan. You're on the thing there for hepta. What was 5?
Penta.
Yep, pentagon. Now we get to the last couple. Do you remember 10?
Deca.
Yep, for decade. And 9?
I want to say Nova something. But it's not.
Yeah, you're close. You're close. Nona.
Oh,
That's
Nona.
right. Right. Now, those are going to be familiar because that's how we used them for naming those binary molecules. But the first 4 are going to be ones that are going to be interesting because the first 4 actually go by the prefixes of meth, eth, prop, and bute. Now, the reason why these stopped doing the convention is because we had names for these types of hydrocarbons long before we knew what they were. And once we discovered what they were, and before we actually had a naming system, we basically just kept the names, okay? So it's kind of like an irregular verb. You use it enough, it just becomes canon. So let me just set this up because I did. Oh, look. How many carbons are here? 2. And the prefix for 2 is?
F.
Yeah.
Right? And so it is named F, and then you ask yourself, is it a single, double, or triple bond? Well, I saw a double bond there, so it's ethene. I have 3 carbons. Its prefix is pro, and so I go, oh, pro. Oh, there's a double bond, propene. There's a reason why that's propene, and this guy right up here with 3 carbons is propane. And that's all we're going to do. So we're going to name the longest chain. And then, if there's a double or triple bond, there is a double or triple bond. Begin numbering the chain. Begin numbering the chain. starting with the carbon. Starting with the carbon closest to the double or triple bond.
Without looking back at all these, are all,
Hold on, Reagan. Reagan, you went in and out. Say it again.
oh, sorry, I think I know my answer. All the double or triple bonds that you've done, whether it's ine or ene, have been on the carbons, correct?
It will always be on the carbons. You can't double
Always
bond
on-
anything else.
Oh yeah, it can't go on hydrogen. Okay, thanks.
All right. Start numbering closest to that bond and tell me where it is. So I'm going to not put the hydrogens. I'm just going to do the carbons only. So actually, I should put this under examples, right? I should say examples. So let's say that I just have, and I'm going to say not putting in hydrogens. They are implied. We're going to assume that we have hydrogens around these carbons. The carbons are the important part here. So let's say that I have 5 carbons as such, all on a nice little line, all single bonds. So that is my chain. I have 5 carbons, and 5 carbons means
Penta.
right? Pent or penta. And then I ask myself, is it all single or is there a double or triple bond?
No.
Okay, so if it's all single, then it's pent
Okay.
ane. You're telling me that it's an out. But if I do CC double bond, C, C, C.
Maybe pentene, right?
Oh, sorry.
Butane.
Oh, butene.
Did we lose him? I think we lost him.
Yeah, I think we lost him as he's not replying.
Oh,
Janet Sandoval's the host now.
no, Forrest is still here.
Well, no, Forrest just came.
Oh, never mind.
No, you were holding the torch there for me for a second. So I don't know where we last left off.
What happened?
Do we have the 5 carbons with the double bond on there?
Yeah, we got pentane. We're at butene.
Not
Oh, no.
butene.
Another C.
Pentene, right?
That
It is
changes.
a pentene, that is correct. But now we have to tell us where that pentene is. So let me get my little participant list over here again. Sorry about the disruption. Thanks for hanging with it. So you're right, this is a pentene. But where is that double bond? Well, I'm going to start numbering the carbons. 1, 2, 3, 4, and 5. Because I'm going to start numbering closest to the carbon that is closest to that double bond. And if I do that, and I start marching my way along this chain, I find that my carbon, the second carbon,
Did you just go out again?
I think so.
Oh,
I think the rain affect this connection.
Are we back again?
Yes,
Yeah.
we're here.
Oh, man.
Was it the rain?
Right. Or do the Zoom gods just hate me? All right, so get back in here, share the screen. Bam. Get my participants up. All right, when last we left our intrepid adventurers, they were saying that this was a pentene, but we needed to figure out where that ene began. So we numbered our carbons 1 through 5, starting with the carbon closest to the double bond. We start walking our way down that chain, and we see that the double bond occurs on that second carbon. So what we do is we say that it is 2-pentene, meaning the second carbon is the one that has that double bond.
So, question.
So,
The two have to be before or at the end.
what do you mean?
Is we have to put the two before the pentene, or we can put that in like pentene 2 or 2-pentene?
This is how it's done.
Oh,
There is no other can we X, Y, and Z. This is, and that is it. Absolute.
all right.
The rule is inviolate. Okay. So what does that look like with something else? What if I have C to a C to a C to a double bond C, C, and a C? What do we have here?
The number changed to 3.
Okay. 3 what?
What's the name?
3-hexene.
Yeah.
That's right, 3-hexene. And you'll notice here that it doesn't matter which way I go, right? If I go 1, 2, 3, or if I go 1, 2, 3, it won't matter. So just for you, Reagan, this could also be isohexene because it's the same on either side.
Oh.
So it doesn't matter on that case. Just so you know, you could have this, C to a C to a C to a C to a double bond to a C to a C. In that case, Bethania, or Brenda, or Daisy, or Dominique, or Emily.
It's 4-hexene.
Is it 4 or is it?
Yeah, it's 2.
Aha!
Start to the closest.
Yeah. So now here's the thing. You know, you fell into the trap just like I asked you to. No, it's going to be 2-hexene because we're always stuck on thinking left to right, and that is not how it goes. It's whichever side that double bond happens to be, start numbering. And there are reasons that you would write the double bond either on the left or the right side. It depends on the reaction you're trying to do. If you want to put that double bond closer to the other molecule or not, is usually the reason why you would, quote, flip it around. But just be aware that we all probably agreed that it was a hexene, but it is 2-hexene, not 4-hexene. So it's not 4-hexene, because you can get there off of that second carbon. It just happens to be on the right, and that's okay. What if we have C, 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 triple bond C versus C, C, triple bond C, C? So clearly with 4 carbons, what is our root?
Pro.
Yeah, prop. So we got a prop. And of course, now with our triple bond, it's going to be prop.
Ein.
Propine.
Did I confuse those? Prop and butte?
Methyl, ethyl. Oh no, yeah, you're right. You're right. No, I completely just listened, didn't count. Sorry, you're right. It's butte.
Okay.
Sorry about that, guys. Even I was like, yeah, of course. So the methyl ethyl propyl butyl, that's just something you got to practice with. I'll tell you right now, that was one of the banes of my existences. If we were actually in class, you'd probably watch me counting on the back of my hand. Because one day when I was trying to learn it, I don't know why, but I just started tapping the back of my knuckles and saying methyl ethyl propyl butyl for the 4. And so oftentimes, even to this day, I would count on my hands to make sure that I was naming it correctly. So 1, 2, 3, 4 should be methyl ethyl propyl butyl. So it should be butte. There's a triple bond, so it should be butine. Good catch, Reagan.
Thanks.
Now, where is that triple bond? After which carbon?
The first.
The first.
Starting from the right, yeah, 1.
And on the second one?
Well, it could be 2, but it's also going to be an iso because it's even on either side.
Right, but I'm not going to hold you to isos, so 2 is fine.
Okay, 2.
And of course, that one, it didn't matter which way. Now, this is as hard as it's going to get, guys, for this part. Are we okay? You're going to have to name 1 or 2 of these.
Yeah.
Pretty straightforward. All right. It's one thing to be a hydrocarbon chain, and it's another thing to have a purpose in life. So I want to talk about functional groups. All right, these give hydrocarbons a function. It makes them useful for something. These give hydrocarbons a function. Makes them useful for something. Besides burning. Okay, and we've already seen one already. If we scroll up real quick, and I did the whole isomer thing for Reagan, you notice that I started putting something new besides hydrogens and carbons together. I started putting other things on there. This actually gives it a function. This right here is acetic acid. This right here, that group that I just circled, is a carboxylic acid group. That gives it the vinegary aspect that we want. Much better than trying to drink ethane gas. It's kind of put other things on it. Give it a reason to live or be ingested. All right. There are going to be, what, 9 or 10 of these. The first one is going to be the organic halide. The organic halide looks something like R to an X, where R is some hydrocarbon chain. I don't care what, it's just a hydrocarbon chain. And X is halogen, hence organic halide. Boy, my handwriting is like horrible today. Today, I beat you to it there, April. So it might look something like R to a Cl, or a CH3 to a Cl. Now, these guys are useful as a precursor to organic synthesis. So let's say that you had something like methane gas, which is just CH4. If I wanted to turn that into methanol, wood alcohol, an easy way for me to do that is to pop one of the hydrogens off and stick a halogen on there. And that halogen can later be replaced by an alcohol group much more easily than trying to replace the hydrogen. So this synthesis is usually a first step in trying to get a more useful thing on there, at least useful as far as humans are concerned. Now, organic halides do have a place though. Teflon is an organic halide, and it helps things not stick to our pans. But that's pretty much all it's worth. Next, we have the alcohol group. The alcohol group looks like some sort of chain to an OH. Examples of this might be just what I was saying, CH3OH or CH3 CH2OH. Now these could also be written as, if you wanted, they could be written as COH or CCOH. So there's the long version and the shorter version. Now the key here is that in each of these, you'll notice that I don't care about the hydrogens, I don't care about anything else. I only care about the important thing, and the important thing is what makes this different than a standard hydrocarbon chain. And in this case, it is that you have that OH group. I'm going to put one more up here for you. Let's see, it's going to be CH3, CHOH, CH3. 4. Now, if we look at these groups, they have some sort of hydrocarbon chain. I don't care about the H's coming off of it. All I care about is that functional group, in this case, the alcohol group. This guy right here with only one carbon is called methanol. One carbon, methanol. 2 carbons, Stuart.
Butte.
2 carbons means,
Butte.
oh no, 2 is F.
Oh, sorry.
So that becomes ethanol. Reagan, 3 carbons.
Propanol.
Okay. Propanol. Now I'm going to actually tell you that just like with the double and triple bonds, when you get to larger carbons, you got to tell me where that alcohol is. So why don't you go ahead and do that by extension from our original naming? What is the name of this one? Which carbon does that alcohol group show up on? Oh.
It's gonna
I'm
be
gonna get
2-propanol.
Oh, good. I didn't get dumped. Yes. It's 2-propanol, or as we all know it as.
Hello?
Oh, he's gone.
Yeah, isopropanol.
Isopropanol. I thought it had to be a double.
So I'm doing a little backdoor here for you guys to at least tell you what's going on. Obviously, third time I've been dumped. I messaged my guy, and he messaged back, said the entire network just took a collective dump. He's looking into finding out why it did it. Sometimes this can go quickly. Sometimes not so much. So I would say if you guys are comfortable just sort of hanging out for a few minutes, because I assume who's hosting it?
I think
Sandoval.
Sandoval. Wow, you like getting dumped off. That's like the second or third time you've been my host, huh?
Yeah.
Okay. Yeah, I mean, if you guys don't mind waiting, just in case it's just a simple matter of the guy like remodulating everything, I guess we could sort of hang out. Maybe even I'll hang out with you, and then at a certain point we might just call it. And if we do call it, then I'll wait till the internet's back up, and then I'll blast out another message to you guys to finish it. We're actually very close to finishing this lecture. I really wish I could get on there to finish it. Actually, I mean, we could be very bold, and we could transfer over to Meng, and Meng could start writing stuff because she's got these notes. Or we could wait. What do you guys want? Do you want to go the super bold route, or do you just want to hang out for a minute and see if it gets fixed?
I don't really mind. Whatever's better.
Oh.
Well, why don't we wait a few minutes and see if they get it first, and then maybe we'll try the bold method. Or if it just is going to be down, then maybe I'll just try again in the afternoon or something, because we are seriously almost done.
Go bold. Melinda kicks ass.
Doesn't she?
Yeah, I say we wait 30 seconds and then go bold.
Wow, we aren't even going to give me 5 minutes. She's like, screw this guy. Let's go with Melinda. All right.
I agree.
Well, we can do it. Melinda, do you have your old notes up or out?
I can get them.
Because it looks like you might be put on deck.
Okay.
Look at this. Okay, it reminds me of one of those. So I got a message back. He says they're trying to get it back up right now. So it may end up. This reminds me of Star Wars, where it's where Vader force chokes the one guy to death and then just instantly promotes the other guy. He's like, oh no, you're Admiral. It's like, oh, thanks. I'm sure that's how Meng feels at the moment.
Unwelcome promotion.
Somebody just said something, but it was quiet.
Somebody said something, but it was quiet.
Yeah.
Tell them to speak up. Yeah, who died? Because I think it's Admiral Diet is the guy that gets promoted. Who's the guy that got choked?
I
You don't even
can
check
Google
my
it.
Star Wars trivia for me? I don't have the internet.
Sorry, I like Star Trek better.
What's that again?
I said I prefer Star Trek over Star Wars.
Get out.
Oh man, fighting words. Next, but see, if you're gonna say Star Trek, then you have to actually go in the order of your preference of your Star Treks.
The guy who got choked was Richard Lepartinier. I don't know how to say it.
Is that the actor or is that the character?
Oh wait, no, that's the actor. Admiral Mahdi.
Right. Okay. But wait, my Star Trek person, you gotta say, are you old school, TNG, Deep Space Nine? Those are the only accessible answers, just so you know.
I can't really pick a favorite. I just really enjoyed I don't know. It's Star Wars is just a little confusing, like with all the different. I don't know. It's kind of hard to explain, but I mean, I like both. I grew up with both, but I just prefer Star Trek a little more.
Fair enough.
I've not watched either one.
April,
You have homework to do.
I'm not into Star Wars.
I'm not mad. I'm just disappointed.
I've never seen Lord of the Rings. I've never seen any of those.
I've never seen Harry Potter or any of that stuff.
Oh my god.
Nope, never watched Harry Potter.
The closest thing to like fandom stuff I'm into is like Marvel, but that's like as far as I go.
Marvel's good.
Yeah.
Marvel's just an action flick. April, seriously?
Yes. Seriously.
You guys are
God,
missing
what do you
out.
watch? What do you? Crazy talk. All right. It looks like Meng's gonna take us home. Okay, so I am gonna go ahead and I think I can still continue on in my notes as we do this. I don't know that it's gonna be. It won't be my voice or anything necessarily. It still might be a little bit, but so I wanted to point out. Yeah, I'll just keep going with the notes and seeing what happens here. So if you notice, each of these methanol, ethanol, propanol alcohol groups end in. I assume somebody screamed out, "Oh!"
Oh, yeah.
Yeah, good. So yeah, you'll notice that each of these alcohols end in "all." That means that they have an alcohol group on them. So these will end in "all." So, oh shoot, you don't know what I'm typing, Melinda. So I underlined the OLs, and I noted that they all end in "all." And I'm going to put in parentheses, this includes cholesterol. This includes cholesterol.
You guys can see my screen, right? Just wanna. Okay.
You can see it.
Yeah.
Yeah, we could see it.
Cool.
So, yeah, and we all know that, alcohol or ethanol does its thing. Wood alcohol has been used as a preservative. That's the methanol, and we all have isopropanol in our cabinet. Each of them have that alcohol group. That alcohol group can do different things to our bodies depending on what we're doing. Methanol will essentially make you go blind. Ethanol will, have its effect, and isopropanol will disinfect things. Cholesterol also has an alcohol group or more on it, but it just happens to be attached to a very, very long hydrocarbon fatty chain, which is why cholesterol will still not be soluble in your bloodstream and still clog everything up. All right, Meng, are you on colors, right?
I have colors available. I don't know what to color code though.
Well, now you're back to black, and we
Okay.
have the topic of ethers.
Okay.
Wait, before we jump there, Forrest, I just have a question. So we ended with propanol, and
Yes.
I'm confused though because we gave it a 2-propanol, but I thought we only did that when we had a double or triple bond.
Oh, so we must have cut out just as I was saying that.
Yeah.
So it turns out that when you have a functional group, you have to tell me where that functional group is, just like you would tell me where the double and triple bond is, which is really fun when you have both double and triple bonds and functional groups. Then the names get really interestingly long. I always, in a normal semester, I would also say, look, some of these names get long, complicated, and bizarre. I worked with a surfactant in my graduate work, and its name was bis-2-ethyl-hexyl-sulfosuccinate sodium salt. And every single bit of what I just said there, you could reconstruct that molecule based on how it was named, but there's a lot in there. So even if I had this 2-propanol, I could actually do this with 2-propanol by taking one of those carbons and making it a double bond. And you can very quickly see how this can get ugly real fast, which is why I'm not expecting you guys to know much more than how to name the anes, enes, and ines. and at this point, how to recognize the functional groups. I will not be making you name things with functional groups. You'll just have to recognize the functional group. Does that make sense?
Yeah, and you called this isopropanol, and the iso came in because it was on the second C, which it was 2, whether you started from left or right?
That's correct. And
Okay.
I only point this one out because we're all familiar with isopropanol. But
Okay.
if you go and you buy isopropanol at the store, there may be companies that say, we're going to call it what it should be called, 2-propanol. And, they are the same thing.
Okay, and then I have another question.
There are certain
Okay.
names from antiquity that we just sort of hang on to because they're there. But the iso is slowly going out of favor, except for things like isopropanol or isobutane, small ones where the name will just stick. But for the most part, the convention is going to the numbering.
Okay. And then we learned this in bio, but we call it the hydroxyl group. Is there why is it named one thing in bio and something else in chemistry?
Because, we can't always agree. You're right. It is a hydroxyl group, but it's also an alcohol group. And so, yes, chemistry and bio call them different things. And in fact, if we get to the end of all this, I'll show you why. I'll show you another place where we call them 2 different things.
Okay. Thanks.
Just rechecking if I have any internet while we're here, because hopefully I can join back into my own thing. So, just in case, wait for it. I have speed. Hold on. Let's see if I can jump back in. Oh, this would be cool. All right. Shoot. How do I join? Ooh, can I go back to my own thing here? LaunchCon for Zoom. I can host that. It's going live right now. Let's see if it lets me in. Open the link. I'm surprised he didn't shoot me a text saying we're up and running. I just happened to accidentally. Boosh! Am I in?
Wait, am I in?
Yep, you're in.
And Melinda dumps out before we all go crazy with the echo. Hey, Mang,
Yeah.
stepping in.
Mm-hmm.
And thanks, guys, for hanging in there. So this is what I wrote. Is that pretty much what she had?
I didn't have as many examples from 110 when
Oh,
I gave just methanol and ethanol, but
okay, that's fine. All right, so next we have the ethers here, guys. This will look like some sort of carbon chain to an oxygen to some sort of other chain. The R prime is another chain. I need to get my participant list up here so I don't go too far away. Hey, where did we get 24 people all of a sudden? Oh, we started with 22. Somebody came in late. I like it.
that was me, sir.
Who's that? Oh, Massey? Oh.
Yeah.
Cool. All right. So these might look something as such. CH3 to an O to a CH3, or CH3 to an O to a CH2, CH3. Or if I just want to go ahead and draw something like this. Ethers, they have the hydrocarbon chain broken up in the middle somewhere by an oxygen taking the place of the carbon. And of course, when it's in the middle like that, it's going to bend the chain, as you can see down there on the bottom. And these will have names like dimethyl ether or ethyl methyl ether or diethyl ether. And Massey, since you came in late, I'm going to make you answer this question. Do you notice anything about how they're named?
Yes.
What do you see?
The prefixes?
So I was going to go with this.
Oh, well, yeah, that.
Ether. So when we have that, it'll tell us, oh, we have an ether. Oh, we have an oxygen. Now, the other thing that you might notice, and you're talking about the prefixes, is a little bit less than that, is these guys right here. Ethyl, methyl. First of all, it's named with the pieces on either side of that. And we can see that we have an ethyl group, 2 carbons, and a methyl group, 1 carbon. Now, for those who actually work in the manufacturing side, this is also known as methyl ethyl ether because that's how they used to name it, was the number of carbons. They've since named it alphabetically. And hopefully you guys can see that on this guy, since I have the 2 carbons on either side, both are ethyl groups. We just say it's diethyl, just as in the top one, it's dimethyl, because it's just a 1 carbon. Now you'll know it's an ether just because it ends in the word ether. And you just know that somewhere in there, there's an oxygen. And what an ether is going to do is tell you what's on the left and the right-hand side of that oxygen in alphabetical order. Now, ethers tend to be very volatile. These are very volatile, which means they have a high vapor pressure and they get in the air very quickly. They're very volatile. And this diethyl ether, by the way, was one of the first anesthetics. Anesthetics. It was one of those compounds that was discovered. And what was really interesting is all the super elites were having a lot of fun with it. Essentially, it was whippets for them. They would take a cloth, they'd dump this onto the cloth, and they would hold it in front of their face, huff the vapors, and get all super happy, not unlike nitrous. The side effect, though, is that when people would start fumbling around and whatever, and they'd bump into tables, they would just laugh it off, and they wouldn't even seem to care. And at one point, some physicians said, wait a minute, this could be good. And it turns out that your first anesthesiologist was born. You had to go in for some sort of very unpleasant circumstance. You would go in there, you lay down on the table, somebody next to you would have a bottle full of this stuff, put it on a mask, or a cloth, put it over your face, knock you out. Doctor would start cutting. You'd start waking up, they'd put it over your face again, knock you out. They'd keep cutting. You'd start waking up, and you just keep going about on this. And if that sounds a little barbaric, technically that's what your anesthesiologist does today. They just do with that different drugs, and they monitor you slightly differently. If they see you starting to come out of your sleep, they just boom and put you right back under. That's why you should be very, very nice to your anesthesiologist. All right. Next, we have the amines. This is some sort of hydrocarbon to an NH2 group. Examples of these could be CH3 or CH3, CH2, stuck with the NH2 on the ends. And these guys would have, let me just do this real quick. These guys would have the names of something like methyl amine, or with 2 carbons, ethyl amine. Now the amines with this nitrogen group on the end of it has some very interesting properties to it. And hopefully it doesn't take too much of an imagination to note that all amines end in amine. That's how they get their names. Now, what's attached to them? You just name that chain and stick the word amine at the end. So there's methylamine, ethylamine, you can keep going up, right? The interesting thing about amines is these are bad smelling. And these guys have things like, actually, it's not amine, actually. Let me be very, very clear. It's less the amine and more of the ene that we're looking for. You'll see right now in this guy. Bad smelling is cadaverine and putrescine. These guys ending in I-N-E. One of the first places they found this nitrogen-hydrogen combo on the end of chains was, well, I hope you guys can figure this out. If the names are cadaverine and putrescine, where do you think they first discovered them?
Dead bodies.
Autopsy.
Yeah. Corpses, right? They found that when things died, the cadaver started off gassing some really nasty smelling things. And some of them were putrid, hence putrescine. But each of these had the fact of some sort of chain ending in an NH2 coming off of it. Next, we have the aldehydes. This is some sort of chain to a CHO group. And this would be something, I'm gonna go ahead and just put this out here. We got H to a C to a double bond O to an H. We built this one in lab. And maybe this sort of carbon to a double bond to an O to an H. It's this functional group right here that we're looking at. Technically, this name is meth, one carbon, methanal. The next one is ethanal. Because aldehydes end in al. That's the new naming that they're starting to go to. But we also know these under other names. This guy is also called formaldehyde and ethaldehyde. And so this aldehyde used to be, and still is, an acceptable way of naming things. So these guys will end in al. Hold on, let me write this up here. These will end in ene. And these will end in aldehyde or al. I'm making my A the old school A just so you don't confuse it with the ol for alcohol. Side note, formaldehyde, you notice there's only one carbon. This also had the name of methaldehyde. Maldehyde. But it's given the name formaldehyde for the same reason that you'll see formic acid in just a moment. That formula will come when we see the carboxylic acid. We're gonna tie it back into the formaldehyde here. Okay, so far, we've looked at a few of these. We have the organic halide, just stick a halogen on there. Alcohol group, put on that OH. Ethers, stick an oxygen in the middle. An amine, stick an NH2 on the end. And aldehyde, make it a CHO. Each of these makes a different functionality. Formaldehyde, ethaldehyde, these guys are good for embalming people. So once you get through all of this amine of them smelling bad, now we'll just preserve them.
Hey, Forrest, I have a question. I think you said stick it on the end or put it in the middle. Do each one of them have, like for the aldehydes, they're usually at the end, right? You usually see
They're always at the end.
They're always at the end. Okay.
Yeah, you can't put them anywhere except the end.
So at end of chain. Okay. And then nitrogen group or the amines was in the middle.
They can be anywhere. You notice
Okay.
on the ones I gave you, they're at the end, but you can put amine groups in the middle of things.
Can go anywhere. Okay.
But the aldehydes have to be at the end. There's no way of continuing the chain past that. Because that leads us to this guy, and that is the ketone. And this is some sort of R to a CO to a different chain. Doesn't matter. I'll give you a couple of examples here. We'll have this guy and this guy. The top one will actually have two names here in just a second. The bottom one will have one. Now, just like any other hydrocarbon chain, even if you have a functional group, it is named by the number of carbons. So in the first one, we have 1, 2, 3. That is prop. It looks like propane, but it's going to be called propanone. Ketones will end in -one. So the next one is methyl ethyl propyl butyl. So this is but and -one. But just like with a functional group or a double bond or whatever, you have to tell us where it is. This one would actually be on the second carbon. Just so you know. There you all. Now, ketones are kind of interesting because essentially that oxygen can stick up off of the back of the backbone of the hydrocarbon chain anywhere it wants. At the end of it, if it were at the end, it would be an aldehyde. Notice that the only difference here between a ketone and an aldehyde is a ketone continues that chain on a little bit. An aldehyde terminates it. Now, we do know this guy right here, and better known as acetone. And I'm going to circle back to that formaldehyde and this acetone here. Well, actually, right about now. So you'll recognize a ketone because that oxygen is all alone on the top of the backbone. You see right there, especially in the butanone here, that is sitting all by itself on the backbone of the guy right there. So there's your ketone group. Just want to double check here real quick. Okay. All right. Now I want to talk about the carboxylic acid. This is some sort of chain to a COOH. Examples of this might be an H to a C to an O to an OH. Or a CH3 to a COOH. Yes, Daisy? Oh, that was probably an accident. Or was that Dominique? Now somebody unmuted for a second. All right. If we take a look at this, this one has one carbon right here. So its prefix is going to be meth. And it's going to go methanoic acid. And it's going to be this anoic acid that will tell you that it's a carboxylic acid group. So these will end in anoic acid. In the case of this one right here, we've got two carbons. So instead of meth is ethanoic acid. And the meth and the eth are telling you how many carbons are there. Now, we actually do know both of these under different names. This is called formic acid. And the other one is good old-fashioned acetic acid. Now, formic acid and acetic acid are the more ancient names for these. Since we've gone to a more formalized nomenclature since then, we have now gone meth and ethanoic acid. But those old names will obviously never leave our mind. Now, acetic acid, this comes from vinegar, and the acid actually refers to the two carbons here that we see in the ethanoic acid, which, if I go up here to acetone, there's the two carbons, the 1, 2, off of the ketone group. That's how it got its name, acetone. And if we go up here to formaldehyde, it's because there was only one carbon here. And this, by the way, is also called acetaldehyde for the two. Now, the formic is kind of interesting. I like telling this a little bit here. Formic acid is given its name because it was one of the first organic acids discovered, and it was discovered in the ant bites that you receive. It's not their pinchers that get you so much as the fact that there's actually this methanoic or formic acid on their jaws that actually makes the sting really bad. And we call it formic because the Latin for ant is formica. The more you know. All right, just a couple more left, guys. We just have esters and amides. Esters. This is an R to a COO, R prime. And I'll just give you an example of this guy just for kicks. CH3 to a C, O, O, CH2, CH3. Now, as we look at this guy is called ethyl, ethyl ethanoate. These guys will end in OH. Now, really what it's done is it's told you that this is, oops, I want that in green, that this is the ethyl part, and this is another ethyl part. So we have the ethyl FNO8 because you're looking at this functional group right in here. Now esters, these are usually the good smelling things. So esters are usually the good smelling things. I think ethyl ethanoate might be almonds. I have to double check that. But these are all usually the good smelling things. And I do want to point out that esters have some sort of correlation here to the ethers. If you remember, the ethers had just the O. Where's my ether here? Had just the O in the middle. We're just sticking an extra carbon and oxygen in the midst of it. So they're semi-related in that respect. And the alcohols are related to the carboxylic acid because we're just going to stick an extra CO with it. Let's list the last one here. The amines have a cousin called the amide. And this is just some sort of carbon to a CONH2. And kind of at the end of this, these will end in amide or amide. Now, I told you at the beginning of this, I would tell you exactly what you need to know for the final concerning this OChem thing. But actually, I want to do one little side thing before I do that. Side thing. I'm going to go ahead and put this Reagan. Okay. I'm going to have some sort of R group to a C double bond O OH group. And I'm going to add to that some sort of guy like this, an NH2 to an R prime. On the left-hand side, I have this group. On the right-hand side, I have this group. In fact, let me move those guys over for a second. On the other side of this, they will combine to make an R to a C, O to an NH to an R prime group. They'll do that by these two guys getting together and going away. Now, if we look at the thing on the left, oh, I needed to get that in green. Oops, what just happened there? Let me get that guy back in green. Reagan, what is the functional group that we see on the left? That's COOH.
Oh, sorry, carboxyl. Carboxyl's on the left.
Carboxylic acid.
I was calling it the other one.
Well, the carboxyl group, by the way, remember we called that a ketone, you call that a carboxyl group, right? So you're close. That's a carboxylic acid. The one on the right is?
The nitrogen group, or not nitrogen, amines. It's an amine.
Uh-huh. Now, you've taken a bio class, yes?
Yeah, that's, yeah.
Do you recognize what this bond right here is?
Peptide.
But really, what is this whole thing called?
Probably an amino acid.
And where do you think it gets its name from? Because it had an amine group and a carboxylic acid group.
So that's what it's getting it from.
A peptide bond will make you an amino acid. That's why it's called an amino acid, because it's got an amine group and a carboxylic acid group. That's how it gets its name. I think that's really cool.
That is cool.
I'm glad you liked it because I did it for you.
I know, I appreciate it. It's nice when my classes tie together.
So what do I need to know for the final? Somebody had a chat in there. Are they messing with me? No. AC, getting pelted, nice. All right, so what do I need to know for the final? How about I do this real quick? And I just scroll out. Do you notice anything that sticks out to you in my screen right there? I know it's small. You guys know I'm big on colors.
Oh, the red? Yeah, is it the red?
Yeah, what are the important ones here, guys? What are the ones that basically do what we need to do in our everyday life? Well, we have our alcohol groups. These are very, very important. And I'm not just talking about alcohol. But if you remember back to my sugar molecule that I drew for you guys a few weeks ago, it was pelted with alcohol groups all over it. These alcohol groups allow it to be soluble. These alcohol groups allow for certain chemistries to happen. And it's very important that those things exist on the backbones of these hydrocarbon chains. Otherwise, we wouldn't be able to do cool things like get the energy out of glucose so our brains work. Amines. Aside from that amino acid, can you think of anything that you may have seen in a bio class that has some nitrogens hanging out on it? Do not anticipate the answer. Just say the answer. Do not anticipate. Do not anticipate.
DNA.
Thank you.
DNA.
Right?
Yep.
Now, there's sulfur groups on that as well, but deoxyribonucleic
Acid.
acid, because what's the other thing that's really important?
Acids.
The carboxylic acids. That's right. So what do I need to know for the final? Name a simple chain. And know those important functional groups. And of course, we're talking about the ROH, the RNH2, and the RCOOH, which are the alcohol, the amine, and the carboxylic acid. All right. Any other burning questions? Because
This is burning, but why? Oh, sorry. Why were you putting a dash over the R in some of these?
What do you mean a dash over the R? The prime?
Is that what it was?
It's a prime. That little thing right there.
Yeah. What was that for?
Apostrophe. It just means that it's a different chain. It does not have to be the same. So if you go up,
Okay.
if you go up here, I have a CH3 on one side and a CH2, CH3 on the other. That would be the R. That would be the R prime. Just a different chain. Does not have to be the same.
Oh, it says it right there. R is a different chain. Okay, got it. I missed that before. Thank you.
Oh, I'm sorry. Did I put that for you? Oh, look at that.
You did write it down. Yeah.
So, all right. So any other questions before I stop recording?
No, just go to the end so I can
At
see
the
the
end.
stuff you just wrote for the
Okay.
final. Sorry, thanks.
No, that's fine. Well, then let me answer the question that no one's asking. Yes, we will be around Wednesday. No, we will not cover any new material. Basically, I'm going to open it up at 9:30 as a big, long Q&A for us to do. If you have questions of any sorts, I will absolutely answer them. Otherwise, 9 days from now, we're going to be taking the final. 100 questions, multiple choice. Bam, done. We're good to go.
So when are you gonna publish that one on the YouTube, the video of today?
Whenever it downloads to me so I can upload to it as long as I have internet. So when have I been lax on getting those things up before?
Yeah, because I missed one part, I moved a little bit and I come back in the middle.
Yeah, no, they've been getting better at getting it back to me, but I assume that by mid-afternoon it'll be on the website.
Okay.
And I'm going to post these notes as soon as we're done, basically.
Yeah.
So are we gonna have any type of like formal review, or is it just come to like for the next, until the final, we'll have normal class times where we can ask questions, and Friday mornings too?
Yeah, well, I'll have the chunk carved out Wednesday. I'll have the Friday morning for you guys as well. And of course, if you have questions and I can hop on, I absolutely will. But I don't do formal reviews anymore because when I used to, first of all, it would take 2 hours to do it. We'd be flying faster than you know, and it was kind of pointless. The biggest review you can do is creating your 3x5 card. That will tell you what you don't remember. But there's no point in me saying, hey, look at all the stuff we did, because I can go as fast as I can write and still not get it all in 2 hours. If I were to point out everything we've done with an example here and there, there's no point. You wouldn't be able to write fast enough. You just sort of be watching. So, and on top of that, I didn't want the whole, you didn't go over that in review, because maybe I forgot something. So I do not do a formal review, no.
And it's all multiple choice, so anything, gosh, remember when we did the dot stuff? The dot configurations.
Yeah.
I'm just trying to think of stuff that we would have to draw, but I guess we can't draw anything.
Well, no, you can draw, but it'll say, draw this. What kind of bonds do you see? Draw this. How many lone pairs do you see? Draw this. What's the shape? And you'll do the answer.
Okay, got it. Okay.
Boosh.